Welcome everyone to today's version of our International Inverse Problems seminar. So we are very happy today to have Per Christian Hansen from the Technical University of Denmark, which will be talking about both convergence and non-convergence for algebraic iterative reconstruction method. So thanks a lot, Per Christian, for joining us and giving a talk today.
Thank you very much. I'm very happy to be able to give this presentation. You could think of this as a survey of things that I and some other people have been doing over the years related to the convergence of algebraic iterative reconstruction methods for, with applications in computer tomography, right? So this is joint work with a lot of people, as you can see here, from around the world, from Sweden and from Japan and from the Netherlands and from the US and from Denmark. So, okay, let's get started. Here's an overview of what I plan to talk about. Very briefly, I'll just introduce the model for X-ray computed tomography, and then I'll move on to talk about iterative reconstruction methods. I will start with the stationary iterative methods and say a little bit about their convergence. And then I will move on to other aspects of convergence, such as semi-convergence. I'll try to explain what that is. And then the second part of the talk is related to something called what I call unmatched projectors. Of course, I will tell you what that is. And that can give rise to new interesting difficulties, you could say. For example, non-convergence of these methods here. And I'll talk about what to do, how to fix the convergence. And finally, I will talk about Krylov subspace methods, and in particular, the GMRES method. Right, okay, so just one slide here about X-ray CT. The basic idea is that you send X-rays through an object at many, many angles. You measure the attenuation of the rays due to the absorption in the object. And from all these measurements, you can reconstruct the inside of the object. So the mathematical formulation of this in the case of 2D problems and X-rays that are parallel, the mathematical model there is the radon transform, right? So the notation here is F is an image that represents the object, and the radon transform is basically a way to write all these line integrals through the domain that give you the attention. The output of the radon transform is what we typically call the sinogram, and you see an image right there. So that's one thing we need to think about. That's the radon transform. And then another important piece here is the adjoint of the radon transform, and that is called the back projection. And these will play a big role a little bit later on. Okay, now if we talk, there are so many different algorithms available for doing reconstruction in computed tomography. And I will just mention here two different ways of thinking about a reconstruction. So one approach is to formulate the forward problem as some kind of a mapping or a transform, and then to do the reconstruction, we should find a stable way to invert that transform. So for example, for two-dimensional parallel beam tomography, that's the radon transform. And when we implement the inverse radon transform, that is called the filtered back projection method. Okay, so these transform methods, they can be very fast because very often you can implement them by means of fast Fourier transforms. And if you have lots of good data, then they can give amazing results. Unfortunately, they are kind of tailored to specific measurement geometries. And if you have less data or if you have noisy data, they may not perform so well. So for that reason, people have been looking at other algorithms. And in particular, I'm interested in the algebraic methods. And here what you do is you discretize the forward problem. You set up a linear system AX equals B, and then you solve that system. So A will be a matrix that represents the forward projection, say the radon transform. The right-hand side B represents the measured data, so that would be your sinogram. And then the vector X represents the image that you're trying to reconstruct. Okay, so how hard can that be? Well, typically this is a very large problem, so you need to use an iterative method in order to solve it. And on top of that, the matrix A can be quite ill-conditioned, so we have to be aware of that. The nice thing about this approach, though, is that it works for any measurement geometry, so it's very, very flexible. And in particular, it seems to work quite well if you have limited data for various reasons. Maybe you're not able to measure, doing measurements all the way around the object. Okay, so this has its advantages, but then we have to think about how to deal with an iterative method here. So for this talk, the first part of the talk, I will basically think about the Landweber method that you see right there, the steepest descent method. There are many more sophisticated methods, but this will be good enough to illustrate the points I want to make about convergence. So so let's stick with that. Okay, and here is an example of convergence. This is just a simulation. This is a test problem where my test image is inspired by the Dutch cheese that you can see right there. So a colorful reconstruction. And here you can see the iteration vectors when I run Landweber on the project there. And I hope you can see as you're doing more and more iterations, you get a better and better reconstruction, because the method will actually converge to a least squares solution, right? So anyway, as I mentioned, when we are talking about iterative methods, we need to deal with convergence. What does the method converge to and how fast does it converge? Then when we have noisy data, we observe something called semi-convergence. I will explain that. And then as it turns out, we sometimes face non-convergence. Okay, so I will get to all these three issues there. So convergence, all right. So this is a bit of convergence theory for Landweber's method. If you look at that, you see we have an upper bound for the reconstruction error after doing k iterations. So what I assume here to make the notation easy is that actually the matrix A is square and invertible. And then we have this relation here for the convergence. So this is like a classical result, and you can find this in many texts, right? Linear convergence is what we have here. And we can also see from this expression here that the convergence can be quite slow when you have a large condition number. Okay. So anyway, I will not say much more about convergence. There are lots and lots of results in the literature about the convergence of these methods here. I'd rather talk about what happens when you have noisy data. Okay, so as I mentioned, for the algebraic methods, we set up a linear system of equations. And then in principle, we want to solve that, right, to get the solution. But unfortunately, when A is ill-conditioned and we have noisy data, this is probably not what we want to do. So here's my notation. Oh, this is a busy slide. Essentially, my measured right-hand side is some true data here coming from a forward projection of the ground truth image or the exact image. And then on top of that, I have the noise, right? So if we compute what I call the naive solution right there, well, what happens? You do A inverse times the noisy data. You plug in the noisy data is of this form here, and then you see the naive solution is actually the exact solution plus this term here, which I call the inverted noise. And this is the bad guy here in the equation, because when A is ill-conditioned, then typically this vector here will have elements that are much larger than the elements in here. So in the naive solution, you may not see the true solution, you just see the inverted noise. So we have to deal with that fact. And of course, this is why people use regularization methods in general. Those are different ways of dealing with the noise. Okay, so in this case here, we apply an iterative method to solve AX equals B. So let's look at what happens here. Now, what I plot here is the reconstruction error as a function of the number of iterations, right? So let's see. So remember, X bar is a true solution. That's the exact solution. And XK is my iterate when I apply an iterative method to a problem with noisy data. And what you can see here is that first the reconstruction error goes down, and then it starts to increase again. So initially it moves towards the exact solution, and then it deviates again, because it eventually, this method here will converge to this naive solution here that we don't want. But along the way, it seems to be doing quite well here. Here you can see reconstructions for different values of the number of iterations. And you can see what happens, that in the beginning, things are going well and we do get a better and better reconstruction. But then at some point, you can see that noise starts to creep into the reconstruction. In particular, you could see it here in this little region of interest here, which is just a part of there. So what is going on here? Well, this is what we call semi-convergence, okay? So in this iterative process, we have two different stages. In the initial iterations here in the blue part of the curve, the iterates actually approach the exact solution. And then later on, it starts to converge towards this naive solution that we do not want. So we would like to stop the iterations right there at the transition between these two behaviors. Okay, right. And of course, we can explain this. We can explain why this goes on. The way we do it is that we split the error into two components, right? Both of them depend on the number of iterations. So we split them into a noise error and an iteration error. The noise error is the deviation, as you can see, that's the red guy here. That's the deviation of the iterates applied. These are the iterates applied to the noisy data. These are the iterates if you could apply the method to the clean data, with no noise. And then we have the iteration over here, which is different between these guys here and the true solution. And then it turns out that, of course, the method converges. We have just seen that a few slides ago. So the iteration error here, that's what I plot here, will decrease as you do more and more iterations. But it turns out that the noise error here this component here actually increases. As you do more and more iterations, you tend to absorb more and more of the noise from the right-hand side into the solution. And the total error is then the sum of these two guys, and that's why it has this particular behavior here, first going down and first going up. Right. And yeah, so the way we can analyze this is, of course, by means of this singular value decomposition. And this is certainly not new stuff here. There's a very nice paper by Van der Sloys and Van der Forst where they discuss these issues here. So what we can do is we can, you know, I just see there's an M matrix here in these equations. Forget about M. Think of M as the identity matrix here. So what we can, in terms of the SVD, we can write the kth iteration vector as a filtered SVD solution, okay? And there are some filter factors here in front of that. We're already familiar with that, for example, from truncated SVD or from Tikhonov regularization. And if we plot these filter factors here, they look something like this. They are, of course, a function of the singular values. And this is the size of the filter factors. And then you can see as you do more and more iterations, these curves here are moving to the left, which means that slowly we include more and more SVD components into the solution. So that explains actually why we have a decreasing iteration error here, because more and more of these terms here will approach a 1. On the other hand, we will also include more and more of the noise, because more and more of these coefficients here will be larger. And you see here we have the noise. So as we do more iterations, we will have an increasing amount of noise coming into the solution. So that's what we do in order to explain why we have semi-convergence. So semi-convergence is not a bad thing at all. It means that we can actually compute a reasonable approximation to our solution if we are able to stop the iterations right at this point here of semi-convergence. Okay. I will not say very much about stopping rules right now, but there are stopping rules around. Let me move on now to CT problems. Okay, so storage considerations. When the CT problems get very, very large, storing the A matrix is certainly an issue. So we have to do something else. And what people are doing is that they write functions that will implement the matrix vector multiplications without explicitly forming the A matrix. They will just compute these matrix vector computations on the fly. Okay. And this is what is available in all the CT packages that we have available right now. I won't go into all these aspects here, but I put a little commercial here for a recent book that we wrote about these aspects here and many other aspects. I will skip this slide here. Okay, so remember we have the forward projection. That's the radon transform. It's a linear operator, and there's when we implement that on the computer, there's a corresponding matrix A. And similarly, there's the back projection, the adjoint of the radon transform, also a linear operation. So there's a matrix B that corresponds to the back projector. Whenever we can store the matrices, if we can store A, then of course the matrix that represents the back projector is the transpose of A, right? Because we have the adjoint here. So, but unfortunately in practice, we cannot store the matrices, and that means we have no way to work with the transpose, because it doesn't exist in our code. Instead, we have two different functions, one that implements the forward projection, one that implements the back projection. And the two matrices, A and B, that represent these two operations typically do not satisfy that B is equal to A transpose. So that's what I call an unmatched projector pair. Okay, so I thought it would be interesting to study how that such an unmatched projector pair influences our convergence. Okay, what happens in this situation here? Let me move on. Okay, so again, if we think of Landweber, but in Landweber, we would have A transpose sitting here, but now A transpose is not available to us. We have a matrix B here that might be an approximation to the transpose. So we plug that in here, and then we see what happens. This is what we refer to as a BA iteration. That's just a name we came up with. Now, this is not related anymore to solving a least squares problem. It's not related to an optimization problem. It's a fixed point iteration. So, of course, what we need to ask is what's the fixed point of that iteration? And it turns out that it's a solution to what we call the unmatched normal equation. So that's what you got to do. Whenever you see A transpose, you plug in your B instead. Okay. So what can we say about this? Again, there's some theory that tells us when we have convergence, first of all. So there is a condition on the size of the relaxation parameter you have sitting there. So that's the condition. There's an upper bound for omega to ensure convergence. And another issue is that you need all the eigenvalues of the iteration matrix here, BA, they must have positive real parts. Okay, so that is not a problem if we have A transpose available, because then the iteration matrix is A transpose A, and that's a positive definite matrix, or maybe a positive semi-definite matrix. So basically this is satisfied, but now that we have complex eigenvalues, and we may actually have an issue with that. Actually, let me just skip ahead one slide here. All right, so here's an example that we have created. We're using the software package Astra for doing the CT reconstructions, and we created the two matrices A and B, and then we computed the eigenvalues of the iteration matrix BA. And what you see here, this is the complex plane. Here are all the eigenvalues, but if we zoom in here on the origin, you see we have a bunch of small eigenvalues over here with a negative real part. And then you might say, well, does it really matter? These are tiny eigenvalues there. But what we can see over here is that, unfortunately, it does matter. Okay, so we have two curves here. The red curve here, that's the error history when we plug in to the method a B that is equal to A transpose. Then our method is really Landweber iteration. And then we know we have convergence, and that's what we see. But if we plug in the B matrix here from Astra, satisfying that B times A has these tiny complex eigenvalues here over in the left plane, this is the convergence history that we obtain. So you see, in the beginning, everything is going well, but then from a certain stage, we have divergence, and this curve would just keep increasing, so the method does not converge. Okay, so we need to deal with that. But before that, let me just go back one slide here. Because if we're in the lucky situation that all the eigenvalues have positive real parts, then we have convergence. And in a paper here, in a recent paper with Tommy Elving, we show that we have linear convergence. This is for the the iteration error. And we also give an upper bound here for the noise error, which essentially says that the upper bound for the noise error increases linearly. Okay, so again, that implies that we will have semi-convergence whenever this condition here is satisfied. So far, so good. But as it turns out, in most situations, the matrices A and B that corresponds to the implementations of the forward and back projections that you see in all the software packages I know, that will correspond to iteration matrices with a small number of eigenvalues over there in the left half plane. So we will not have convergence, which is definitely something a mathematician like I doesn't really like to see, a method that does not converge. All right, okay, so rather have convergence. Okay, so what are the options here? Well, you could go to the software developers, right, and invite them over for a cup of coffee, and you could say, hey guys, couldn't you do your implementations such that we have a matched projector pairs? That would be very nice. And then they will say, no way, because then they will lose the computational efficiency. The reason why we have an unmatched pair is that the way you can utilize performance accelerators such as the GPU is to write your code in such a way that you can use whatever you can do fast on the GPU. And the implication of that is that we'll have an unmatched pair. So they will not change their code. And then what else can we do? Well, we can try to use mathematics to see if we can do something about this non-convergence, and that's what I'm going to be looking at here. And again, so I want to acknowledge the basic idea here, which is due to Tommy Elving. He originally suggested this to me, and so this is what you can do. Okay, so you see, this is almost the BA iteration that we saw before, but there's a factor here in front of xk, right? Okay, so if this factor was not there, it would just be the BA iteration, but we introduce a factor here, which is slightly smaller than 1. Okay. Why do we want to do that? Well, first of all, let me just say that if you implement this in your code, it's really simple. It's not something that takes a lot of computations. It's something that you just multiply with something in your computing pipeline. So it's really simple to implement, and it hardly slows down the method. But anyway, what is it that we achieve by introducing basically we introduce a new parameter alpha sitting there? Okay, well, it turns out what happens is that this alpha shifts the eigenvalues of the iteration matrix from eigenvalues of BA to eigenvalues of BA plus alpha. Okay. So you see, again, here are the convergence conditions. Again, lambda are the eigenvalues of BA. Here is the condition. It looks a bit complicated on omega to ensure convergence. And now when we introduce the alpha or the shift, I call it a shift because it shifts the eigenvalues of the iteration matrix, then the condition here is that the shift in eigenvalues should be greater than 0. So basically, you shift all your eigenvalues to the right, such that there will be no one any left in the left complex plane, right? So that's what we do. Okay, and then again we have theory for the fixed point of this shifted BA iteration, that's this one here. And we can say that introducing this alpha here introduces a small perturbation in the solution, but it's probably something we can live with. So we introduce this shift here, which looks like a regularization parameter, but we do not introduce it to regularize the problem. We introduce it in order to make sure that our iterative method actually converges. Okay, right. And the theory here also tells us how to choose that parameter. Is just be large enough that you shift all your eigenvalues to the right part of the complex plane. Right. So that you can certainly do. And I could stop my talk here, but I want to go on because there's something else you could do. Okay. So as I mentioned, with these classical stationary iterative methods, they will refuse to converge, so we have to somehow fix them. But there are other iterative methods around, and we might take a step back and say, hey, why don't we just consider these unmatched normal equations? And they actually come in two forms, either here or an alternative form here. I refer to both of them as unmatched normal equations, and then just find a good iterative method that solves these unmatched normal equations. And of course, the first method that comes to mind is the GMRES method. Right, because what we have here is a square matrix, but it's non-symmetric. So GMS is the method of choice. And then it turns out that if you implement GMRES for either this one or this one here, then you end up with two different variations of GMRES that we call BA GMRES. BA GMRES kind of solves this one here. So you see that the matrix B here acts as a kind of left preconditioner for AX equals B, or you can apply GMRES to this system here and then go from Y back to X by multiplying with B, and then you have the AB method here, right? So I thought that this goes back to work done by Ken Hayami from Japan, and he has written several papers about this. So the nice thing here is that there are no extra parameters that you need to choose. There's no relaxation parameter, there's no shift, you just apply GMRES. And they always converge, well, almost always, right? And there's semi-convergence. There's not a full theory for semi-convergence, but there are a couple of papers here that kind of justify that we have a semi-convergence. Okay. So before talking more about the semi-convergence, I just want to, how am I doing? Show you a few slides here with a bit of theory here. And I won't go through all this here because this is just way too much. But yeah, anyway, this goes back to work by Ken Hayami, right? Where he introduces these two methods here. He describes very carefully which problems we solve. He gives conditions here for convergence, essentially range conditions you can see here. And he also describes what happens with the residual norms, either this guy here, which we can call the least squares residual norm, that decreases monotonically for the AB GMRES method. For the BA GMRES method, it's the residual norm associated with the unmatched normal equations that decreases monotonically to 0. Okay, I won't go into the details here. I should say, though, that these range conditions here, they're very nice to have, the theory, but as a matter of fact, I don't know how to check them in practice when you don't have the matrices around, and they are actually, if you generated them, they would be enormous. So I don't know how to check that, but it seems to work. So that's all right. I should also mention here that both methods actually work in the same Krylov subspace here, this particular Krylov subspace here, but the AB and BA GMRS have different ways to compute a solution, so they produce slightly different iterations. So mathematically, they are two different methods there. Okay, one more slide with some busy mathematics here. The point I want to make here is simply that if you have a matching transpose, so if your B happens to be the transpose of A, then AB GMRS is mathematically identical to CGLS or LSQR. Okay, so in infinite precision, they will produce the same iterates. And the same thing here with BA GMRS. If you have actually a matching transpose, then this method here is mathematically equivalent to a method called LSMR, right? Again, in infinite precision. So that's very nice to have this theory, but let's move on to some computational results here. So here we apply both the AB GMRS and BA GMRS to a small toy problem with unmatched projection pairs. Here's a picture of the reconstruction from the two methods. These are the error histories where we again compare with the exact solution, and certainly you see the semi-convergence. There's a minimum there and there. Okay, all right. So we have demonstrated experimentally, certainly, that we have a semi-convergence. Which method should you choose? Well, you should choose the one for which the GMRS method stores the shorter vectors. Okay, if we go back here, okay, you can see here there's a matrix here BA, and here's a matrix AB, and depending on the size of A and B, either this matrix will be smaller or this matrix here be smaller, and then you probably choose that method here for which either AB or BA has the smallest dimensions, because you need to store these Arnoldi vectors in the GMRS method. But anyway, this is something we describe in the paper. But I mentioned we see we have semi-convergence, and here I want to spend just 2 slides on stopping rules, because if we really would like to stop our iterations right there, wouldn't we? So we looked at 2 methods for stopping the iterations. I'm sure you're familiar with the first one, the discrepancy principle. So basically you stop whenever the residual is of the same size as the size of the noise in your data. And we also tried a more recent method here, which I'm not going into here. The normalized cumulative periodogram is a way to monitor the residual, and the key idea here is to stop when the residual vector looks like noise, because when that happens, then we have extracted all available information in the data. So we're going to look at these 2 here. And just in case you are curious about other methods, well, the L-curve method, it doesn't work for these problems. I don't know why. This just refuses to work. And then there's a great method, generalized cross-validation, that very often works well, but we couldn't find a way of implementing GCV efficiently for these iterative methods here. But anyway, let me show you some results here. And essentially what we see here is, let's see what I have here. AB GMRS and BA GMRS for 2 different, just two different combinations of forward projections and back projections. So the minimum is the circle here, and we want to stop our iterations right there. If we use the discrepancy principle, we stop when we hit the noise level in the residual. Then we have the diamonds here. So we stop a little bit too early. but that's okay because the minimum is quite flat. If we use the NCP method, the normalized cumulative periodic RAM, then we would stop even earlier there. So if you know the noise level in your data, then you should definitely use discrepancy principle. And if you don't know that, you still have the NCP method as a backup. So that's kind of okay. I will not say more about this. I just have a few more minutes left. So I'm going to show you some brand new results. They are going to be presented very soon at an upcoming conference here on X-ray CT. And here we apply the methods to real data. Everything else you have seen so far has been simulations, but here this is cone beam data from a particular scanner where a physical phantom was actually put in the machine, and you would do your reconstructions. So that's what we do. And just, to try different things, we try two different back projectors here. One is your typical unmatched back projector. The other one is actually a filtered back projection, which is a filtered version of the back projection there. So we try both, okay? And here are the results, right? And we are running, we are running BA, GMRS, and we see that we do have convergence. So that's the black dashed line and the blue line here we see over here. This is the least squares residual, and what we have over here is the residual vector for the unmatched normal equations. For this one, I remind, we have a theory that says that these curves should be monotonically decreasing. Over here, we have no theory that we should have a monotonic decrease, but that's what we see anyway. Okay, so it's all very good. And in fact, if for B we use a filtered back projection, we actually have pretty fast convergence. So that would be one way to go. Okay, and then there's one more thing, one more curve over here, and that is the red curve here. Okay, so I write CGLS. Okay, so this is the convergence that you will obtain if you take your code for the CGLS method, right? But whenever you see A transpose, you plug in your B matrix, which is no longer the transpose. So of course the method is no longer CGLS. It does not, there's no theory for what will happen. It's certainly not an optimization method anymore. And as you can see, after some iterations, it diverges. So it's not a very good idea. But the GMRS methods, they work very well. So we are quite happy with these results here for real data. Okay. So time to finish. This is my last slide to sum up. Convergence for noise-free data, there's a lot of results for that already in the literature, so we understand that. When we have noisy data and we have semi-convergence, well, there is some theory, and we're still obtaining more and more insight into when and why we have this semi-convergence that I mentioned. Okay, and then we have the non-convergence, that is something we observe for these stationary iterative methods when we have an unmatched pair of projectors. And we can fix that, as I demonstrated for the shifted BA iteration. There's a way to get these methods to converge. Alternatively, we could use Krylov subspace methods applied to the unmatched normal equations, right? So here you can see advantages and disadvantages of these two methods here. Okay, shifted BA iterations, very simple to implement. There's no need for extra storage, so that's wonderful, but you do need to determine two parameters, and they have to satisfy certain criteria. For the GMRS methods here, well, the Oh, I should swap those two here. Oh, I'm so sorry. They should be swapped. An advantage is that there are no extra parameters. A disadvantage is that you need to store the basis vectors for your Krylov subspace, or you may actually use a restarted GMRS. Okay, so more to look at there, right? So future work in this area here is try to develop more theory about the semi-convergence, and in particular semi-convergence for GMRS. There's still a lot of work to do there. How to deal with storage issues here for GMRS. So restart methods. There's also something more recent called recycling, which I want to get a look at. Maybe there's something there. And then maybe the most important thing is somehow write some good code that the CT community can use for their reconstructions. Okay, let me finish right there.
Okay, thanks a lot, Per Christian, for a very nice talk. A lot of interesting material here. So the floor is open for questions. So please unmute yourself and ask questions if you have questions, either about convergence or non-convergence. So I was wondering a little bit. So you have a choice when you construct in the discretization. So how you discretize the problem. Can you sort of use insight about the noise to help you in sort of having choosing the discretization? How would you choose the discretization?
Oh, that's a very good question. And I actually have one slide that I skipped, and that was this one here. So this stuff is explained in our book, of course. So let's see. So if you think about the physics in the CT scanner, right? Well, you have a detector here that consists of a number of pixels or detector elements sitting right here. And then you have your X-rays going through your domain, and here I have shown the pixels in my discretization. So what you measure in a detector element is actually the accumulated X-rays going through the domain and being damped in the domain. Essentially, you count all the photons coming in here. Right. So this is probably a physically good way to model what goes on in a scanner. That's called the strip model. Unfortunately, it's a complicated thing to implement. There's no efficient implementation of this on a GPU, for example, because whenever this strip here hits a pixel, you have to determine the area of this particular what is that? I don't know. This thing here, all right? So it's not suited for fast computations. Something that the GPU is very good at doing is to compute simple projections. That's why they built GPUs in the first place, so you could play your computer games, right? Where you have a 3D model and then you project it onto your computer screen. Okay, so they can do that very fast, and that corresponds to the line model that you see here. And this is very easy to implement. The only thing you need is the length of this line here within a pixel here. So this is what the GPU does really well. So this line model here, a variance of that, is what is used in all codes today. And then for the back projection, well, people do something else again, because it has to run fast on the GPU. So instead, what you do is you choose a center in a pixel, then you find the line that is orthogonal to the detector here, and then you find that point here on the detector. Then you take whatever is measured over here and you project it back along the green line here, and you distribute it over the different pixels here according to the length in each pixel here. So that's what the back projection does. So this is quite different from the forward model here. So this here is called pixel driven, and this is called ray driven, and that's what essentially is giving rise to the unmatching. That this is giving rise to the fact that the matrices corresponding to forward projection and back projection is the one is not the transposed of the other. So that was, I think, partially answering your questions, but you asked something else, okay? What was that?
Yeah, no, this was very interesting. So, but you also have sort of a choice of the dimension of the matrices, how you would discretize it also.
So that's a very good question. So I have not seen theory for that issue, but it is, hopefully someone will study that issue. What is, because, okay, what is fixed here is the machine and the projection angles and stuff. What is also fixed is the size of the detector elements, because that, you know, that's just part of the machine. There's a sitting at detector in there. What you can choose is the size of the pixels here, right? So you're free to choose how fine, of course, a discretization you want of your image. I can say when I talk to people in CT, what they all say that you should probably choose a pixel size that is of the same order as the size of the detectors. That is based on their, you know, experience over many years. So I have no reason to doubt that this is a good choice, but I have not seen any theory that explains why it's a good choice.
Thanks.
Yeah.
I have a question about the semi-convergence.
Sure.
Yeah. Does that depend on what the noise is, what the vector E is?
It does. That's a good question too. Very often when we do our simulations, we assume that the noise, this noise here, right, is Gaussian noise. Okay, and then we certainly will observe. We will see the semi-convergence that we have here. So is the noise in a CT scanner, is that really Gaussian? No, it isn't. It certainly is not. Okay, so what you measure on your detector is you're counting photons. Okay, so that has Poisson statistics, and then on top of that, you know, to arrive at a linear system of equations, you take the log of your data. So your noise is log Poisson. I don't think that has a name, but that's what it is. But it turns out that unless you have really extreme signal to noise ratios, you can very well approximate that noise by Gaussian noise, right? And you can see here when we do the analysis that the noise enters here. And of course, the nice thing is when you do the SVD analysis, if the vector E is Gaussian noise, then so is the noise in the SVD domain, because you multiply with the U matrix from the SVD, right? So that's an orthogonal matrix, and that preserves a normal distribution. I don't know if that answered your question.
Yeah, it's kind of another way of asking the question is saying if E contains some structures, it's just not random perturbation. Is there some?
So no, in this analysis here, it's random.
Okay.
But certainly you could have another error component, which would be, you could think of that as a background, and then you would compensate for for that background. This is not part of the analysis here, and it's much more complicated to deal with. And then I don't think we could really deal with that with these simple algebraic iterative methods. But people do that. They sometimes do have a background, and sometimes they have a background in their measurements that varies over time, you know, as maybe something gets harder in the machine or whatever, something that varies slowly with time. But then you have to take care of that in other ways. So for this analysis here, my E is a random vector.
Thank you.
Mm-hmm. Mm-hmm.
Good. Any other questions here for Per Christian?
Well, thanks for listening to my presentation.
Yeah.
What I will do is I will certainly, I found a few misprints, as you could see along the way. I will update the slides, and then I will send them to you. Okay.
Well, thanks a lot. Let's thank the speaker once again for a very nice talk, very interesting aspects of the problem.
Thanks.
So yeah, thanks for a great talk.
You're welcome.